This is the second day of the Bayesian Inference for PRA workshop as part of the pre-conference events for the PSAM 16 conference. We stopped yesterday at slide 57 talking about non-informative priors, so we'll start right there. And again, these sessions are being recorded, so your participation consents to that recording. If you have any questions, the chat feature is active. And just as a recap, we talked yesterday about the fact that we need three things to do Bayesian inference. We need an aleatory or a probabilistic model. We need data that goes with that, and then priors for the parameter or parameters in the model. And so today we're going to start talking about special kind of priors. So let's get into non-informative priors. So yesterday we saw cases where the priors were informed. In other words, the industry or handbooks had some kind of distribution on a failure rate or a failure probability or initiating event that carried some information content. And if you have that, that's great. Now there are other situations where you might not be so lucky. You may not have much information. You may be uninformed as a starting point. And so the idea then comes up, how do we represent a case of ignorance or where we don't know anything? Excuse me. Bayes in his work talked about a uniform prior where the probability is just kind of flat across the space. We talked about, in fact, yesterday also Laplace used the uniform priors mainly for mathematical purposes, but used that for many of his calculations when he was doing Bayesian inference. There's some problems with that. For example, if we talk about probability, it may not make sense to say the probability cannot exist below an upper or a lower bound because we may not know. And so kind of having natural tells might be a better way to represent a continuous set of information like a probability. But nonetheless, we're going to talk about how do we specify ignorance. There's several ways to do this, and we'll just talk about kind of the more common way. So a mathematician by the name of Sir Harold Jeffreys looked at this problem and suggested a way to describe a set of ignorance in terms of a prior probability, where even if you changed like the scalar location properties of the information content, it didn't really change the information content. And so we call these non-informative priors. And again, it's intended to be a starting point for a distribution. We need that for Bayesian updating, but not convey very much information. Some people think of this as just a way then to kind of minimize the distribution, but maximize the data. So let the data to kind of drive the problem rather than the prior have much weight into the problem. So that's another way to kind of think about it. And so Sir Harold Jeffreys came up with a mathematical way to describe these non-informative priors, and now they're actually called Jeffreys prior distributions. And it turns out then, depending on the probabilistic or the aleatory model, the prior distribution that goes with that's non-informed or Jeffreys will have a specific distribution type and a specific set of parameters. So for example, if we're going to use the binomial model, and we saw that yesterday when we were talking about the D-cell fails to start, the Jeffreys distribution that goes with that is a beta 1/2, 1/2. If we're going to use a Poisson model, which we did use that yesterday with the D-cell generator fails to run and also the initiating event for loss of offsite power, then the Jeffreys model is a gamma 1/2, 0. If you use an exponential model, we did not use that yesterday, but if you were going to, as a aleatory model, then the gamma 0, 0 is the Jeffreys. Now there's some challenges here already. for example, the last two, the gamma 1/2 0 and the gamma 0 0, those are what are called improper distributions. You're not really supposed to have a gamma distribution with one of its parameters being 0. It's not really defined at 0. But fortunately, the computer codes that we have can handle that situation, can handle a non-proper distribution, and then what we will end up with after we do the updating will be a proper distribution. So it's just not a big deal, but something to be aware of. And how we get around that is we just approximate the distribution. So for example, we could put if we're using the Poisson model, we want to use a Jeffreys, it would be a gamma 1/2 and then a small number close to 0. So 0.0001 or something like that. And then we could also, in some versions in OpenBugs, you could actually just put the 0 in. It's able to handle that directly. It knows what to do with that, so it doesn't stop the calculation. What those first two distributions actually look like, we show here on page 61. So the gamma 1/2 0, we can plot that. It's sort of this almost exponentially looking curve, high peak at around 0, long tail going to infinity. The beta 1/2 is this kind of U-shaped curve, and constrained between 0 and 1, of course, which the beta distribution is. And what we do here is we can have a non-informed prior, update that with data, and as we update, then the more knowledge we get, the more peaked the distribution becomes. And so we show that on slide 62 here, where the shaded curve in purple, called the prior there, the gamma 1/2 0, if we update that, and we do several updates here. So for example, the first update is we saw 1 failure in 10,000 hours. We move from the purple curve to this curve right here. Now, if we update with 10 failures in 100,000 hours, we would go to this curve here. And if we had 50 failures in 500,000 hours, we would go to this curve here. And so what you see is, as we get more data, then that curve is going to get higher and higher and higher, and it's going to be, kind of centered around the maximum likelihood estimator, or 50 divided by 500,000. Excuse me. Okay. So these non-informative distributions are very useful. Again, they're intended to convey the starting point of we really don't know anything about a process. So I have no knowledge about the temperature sensor. I have no knowledge about the diesel fails to run. I have no knowledge about initiating events and so on. Now, that's sometimes the case you're faced with, where you don't really have any information that you're aware of. But there are other cases where you might have some information that you want to bring into the problem. And so, for example, another type of distribution is called constrained non-informative. And what that is instead of just being completely non-informative, you can impose a constraint. And that constraint could be different things. For example, you might know a mean value for, say, a failure probability or a diesel fails to run or initiating event. So you might say, on average, at my facility, I see this occur at 1 out of every 100 demands. And you would like to maybe bring that in. And so there's a way to do that. So constrained non-informative, you can actually build in mathematically the constraint that says, I want to maximize the uncertainty, but I also want to be able to specify the mean value on the prior. We have the ability to do that, and we'll walk through that. You can also specify other constraints. You could say, I want to be able to specify the 95th percentile of the prior, or the 5th percentile, or both. or you could say 95th mean and 5th percentile. So you could get fairly sophisticated here. People tend not to. When we use these non-informative distributions, especially in PRA, we either generally just say we're going to use a non-informative and start with that, or we'll use a special CNI, constrained non-informative, that specifies the mean value. And I show some of the folks here, for example, Claude Shannon there is at the left-hand picture. He did a lot of work on information theory that is based on the non-informative distribution idea is really based on information content. So we kind of owe Claude Shannon the mathematical background for how all of this math actually works out. The middle picture there was Edward Jaynes. He actually did a lot of work on non-informative distribution, especially constraints related to those for mainly for physics, but physical science. And then the third person was actually an INL colleague of mine, Corey Atwood, who developed a CNI prior that is built into code such as Sapphire, and where we can specify the mean value as we do the Bayesian updating for PRA parameters. So we're going to rely on their work. Let's talk about the constrained non-informative then. And in this case, we want to be able to constrain it by specifying the mean value. And so if you look at the math kind of behind this, what it turns out, and this is sort of an approximation, but if you wanted a non-informative prior, that's a beta distribution. And so just to be clear, let me go back a little bit. For the binomial, the beta 1/2, 1/2, that would be a completely non-informative prior. But if we want to specify the mean value for that prior, we have to kind of tweak this a little bit. And so we will still keep the alpha parameter at 0.5, but then since we know the formula for the mean value of a beta distribution, we can solve that equation, keep alpha at 0.5, but we can solve that for beta. So in other words, beta is the thing that's going to sort of be changed. The mean value will be fixed by you as part of the input to the problem. And then beta is just given by that simple formula there. Alpha times 1 minus the mean value divided by the mean value. So pretty straightforward. Similar kind of thing if we're going to use the Poisson aleatory model. The non-informative distribution for that is gamma. We keep the first parameter at 1/2. The second parameter, if you do the mathematics, solve the equation for mean value, it just turns out to be the beta parameter is 1 over 2 times the mean value. Exponential is a little more complicated. The likelihood for that and the prior is not a proper distribution. We can't specify the mean value for that. There are alternative things to do. So, for example, there's a way to maximize the information content, in other words, the entropy. Again, getting back to the Jaynes and the Shannon ideas, but if you want to maximize the entropy, you would use a gamma 1 over a mean value, and that's an exponential distribution. So again, different kinds of ways to specify ignorance, and we'll see some of this when we get into some of the case studies. But so at this point, we have seen informed priors where we use the industry handbooks from yesterday to specify a prior distribution. But now we have ways to specify where, if we don't know anything about a process, we will always be able to have a starting point, because we will be able to use the Jeffreys priors, for example, for the aleatory models that we have. And so we'll always be able to have a way to do the Bayesian analysis. And so we if you can look at a process, describe its probabilistic model, say binomial or Poisson, you have the Jeffreys there always waiting to help you out for the prior, and then all you would need is data. So as long as you have data to support the Bayesian updating, you will be able to do Bayesian inference. Okay. So let's go into then non-conjugate calculations. So yesterday we focused all on conjugate calculations, and recall that that was the case where the mathematics turns out to be quite easy. That integration related to the normalization constant. Um, you can do that integration pretty straightforward. You can write out the answers analytically and effectively just write down the posterior distributions once you know what's going into the problem. Non-conjugates, that's not the case. Non-conjugates are where we're going to have to do the integration numerically, and let's see what that looks like. So, first case here on 66, we're going to have a problem where we're going to, instead of having a conjugate prior, we will throw in a non-conjugate prior. The example here, looking at failure on demand for a pump. So the pump fails to start on demand. Now, yesterday, we would say a binomial model and a beta distribution for the prior. That's a conjugate pair. Now, if I, instead of saying a beta distribution, if I put in any other distribution, that's non-conjugate. So if I say instead of a beta prior, if I say it's a normal distribution or a gamma distribution or a log normal or uniform or whatever, well, except for uniform. Uniform's a special case of the beta, so uniform would actually still work. But any other distribution, it's going to be non-conjugate. And so the example here says, well, instead of a beta, what if we want to use a log normal distribution? Okay, that's just another distribution. It shouldn't really mess us up. We should be able to do the calculation. So let's see how that works. So in this case, I'm going to say a log normal distribution with a mean of 0.003 and error factor of 10. I have my binomial model for fails demand. I need to have data, so I go out and run this pump 36 times, and I see no failures in those 36 times. And then if you do the calculation using open bugs, you will see that the posterior mean value, we move from 0.003 on the prior to the posterior 0.002. It goes down. Why? Because, well, we saw zero failures like we saw in one of the cases yesterday, and we can calculate an interval. But let's look at how we actually do this calculation. I cannot write out the posterior distribution like we could yesterday. I have to let a tool like OpenBugs solve this for me. And to do that, then we just simply go back to the scripting language that we saw yesterday. So in this case, I set up my script. I have a model section and a data section. In the model section, the first line there sets up the binomial aleatory model like we saw yesterday. And again, remember, these are all user-defined variables, so I can name this anything. MDP motor-driven pump dot fails to start FTS. It's distributed as a binomial. First parameter is P, second parameter is N. I call that P.FTS, N.FTS. P.FTS is kind of what I'm looking for, the probability it fails to start. And so I will need to put a prior distribution on that. So I say P.FTS is a log normal, so DLNORM, L norm, log normal. And yesterday on this line, when we were doing the script, we had a beta distribution here. And again, remember that yesterday that was a conjugate case, but today it's more complicated. But you notice the script doesn't get much more complicated. OpenBugs doesn't really care if it's conjugate or not. It's going to just solve the problem. Okay, and then the one complication here is when you move to a new distribution, you have to understand how it's parameterized in whatever code you're using. So if you're using a distribution in Excel, MATLAB, OpenBugs, everybody has different ways to parameterize distributions, and you have to be careful. In the case of OpenBugs, they use a parameter called mu and tau. And you can go into there's a lot of help files related to open bugs. You have to figure out what mu is and figure out what tau is. And so if you look at that, you'll see that, okay, mu is the prior mean, and then tau is actually 1 over the variance, or 1 over the standard deviation squared. And so you see these lines down here, we're just translating the parameters that I have into the parameters that OpenBugs needs. The parameters that I have is this mean of the log normal and an error factor. So one of the first things I need to do is I can change the error factor into a standard deviation of the normal distribution that's related to the log normal. I call that sigma through this formula here. And then of course, once I have that sigma, I can, this is a keyword for taking the power. I'm taking the -2 power, so 1 over the square of sigma. I call that tau. That's what OpenBugs needs for tau. And then for mu, it doesn't need the mean here. It needs the mean of the underlying normal distribution. And so to get that, I have to take the logarithm of the mean minus the variance divided by 2. Again, all of this is just infrastructure to convert from one set of parameters to another set of parameters. I could have just told you mu and tau directly, but that's too easy. And in PRA, normally you'll see things like mean and error factor, actually. And then lastly, I need the data. So I had 0 and 36 demands. I had my, of course, prior mean and error factor. And I'm able then to take a binomial aleatory model with a log normal distribution, not conjugate. Oops, hang on. And so when I do that, then when I run that script on 67, I will see the results that we show on 66. Okay, so we saw how to do that yesterday. Just to repeat, the only difference is we're changing up the distribution. And, you know, instead of log normal, I could have had a gamma there and it still would have been non-conjugate, but again, OpenBugs doesn't care. Okay. Let me move on to another topic. Random durations. How do I model those? So for right now, the models we've been talking about were things like Poisson, which are occurrences in time. So I go out, I wait 10 years, and I count how many loss of offsite power events I have. I might see 0, I might see 1, I might see 10. That's a Poisson kind of approach. I go out and I start my diesel generator 10 times, and I count how many failures I have. That's a binomial kind of a situation. Another situation, though, is I might start collecting data related to, say, light bulbs. I go in and plug in 100 light bulbs in my facility, and I record, okay, I put these light bulbs in on Tuesday, January 7th, 1994. And those light bulbs go for so long, and then one fails, and I write that time down. So maybe that light bulb lasted for 4 years. I replace it and start recording a new time for that one. And then maybe 6 months later, a different light bulb fails. And so I would record that total time. Or maybe what I'm doing is I'm going out when the diesel generator fails. I record how long it takes to recover that from that failure. How long does it take me to fix that failure? Maybe the diesel fails, very easy fix, 10 minutes, it's back up and running. Maybe I need an order part, so it's out for 3 weeks. Maybe the next time it's just a couple days to repair the diesel. And so that would be an example of a different set of data where I have times to something, times to repair. And so if I have data like that, I can have this idea of random durations. That's simply just a different kind of aleatory model. And so, for example, I might put an exponential model on those times to say the repair times for the diesel is distributed by an exponential distribution. I don't know, the next time the diesel fails, it might be 2 minutes to fix it. It might be 2 weeks to fix it. I don't know, some random time. And one of the models we have for that is exponential, and we have others. We'll see some of those actually. Exponential is a very simple distribution, has a single parameter. We call that lambda. The mean time to repair or restore is just 1 over lambda. And again, so we would have these series of times that I record. So this whole idea is described in chapter 8 of the book. And what we end up with is this idea of the red curve here, where I have some phenomena that I'm going to describe as being a set of times. And that's what's the little f of t. So in other words, in this case, it's an exponential model, the red curve. And once I have that, then once I know, how easy or not easy it is to restore or recover a component, or if I know how often light bulbs burn out, if I can specify that red curve, then I can start talking about the failure probability or the recovery probability or the non-recovery probability. I can either look at the capital F of t or the R of t, sort of the converse. In this equation or this picture here, F of t is the failure probability, R of t is the reliability, so 1 minus the failure probability. But again, it all hinges on being able to specify that red curve. And so I need to be able to, take this model for exponential for times, run that through Bayes' theorem. To do that, of course, we use something like open bugs. And so we have to specify an aleatory model, data, and a prior. What does that look like? Well, in this case, it's a little more complicated. Why? Because I have a set of times. So in other words, I have a vector of times, and so I'm going to have to figure out how to describe a vector in open bugs. And fortunately, that's pretty easy, of course. To describe kind of that vector of times, there's this idea of an array. In open bugs, they use a square bracket. So my model here really is saying I have a set of times indexed I to however many times I have, n number of times, index I, and they're all distributed using this exponential model with a parameter called lambda. I'm looking for lambda. That's the failure rate that will give me my exponential distribution. I have to specify a prior. The Jeffreys prior for that, remember, was a gamma 0, 0. And I could approximate that by putting a 0.00010001. So this is an approximate Jeffreys. And then I'm actually also doing a calculation here on the side. I don't need to have this mean time to repair, but you notice you can just do calculations in this script at the same time you're doing the Bayesian updating, which is a nice feature. So I'm actually doing the Bayesian updating on lambda to get what is my posterior distribution on lambda. I'm also calculating the mean time to restore or recover, which is just 1 over the lambda. And the nice thing about this calculation is that it's going to account for the uncertainty in lambda, because lambda is a distribution. Lambda starts out with this prior, but will change into the posterior. The mean time to recover will account for the fact that this is a distribution. So why we'll get a distribution on the mean time to recover. And then lastly, I need to specify that vector or that array of times. And so I have some data here that I just made up, but to specify an array, there's this C bracket, that's a keyword. So whatever variable I have here, which is called time, I just say, okay, time is an array equal to 105, 1, 12, 63, and so on. And I have 14 of those data points. Okay, so what's new here? The concept of array. I can loop through that array with the for keyword. I'm using a Jeffreys prior, and I'm doing a calculation. Now, one complication when you run this, this distribution is a pretty weird distribution on lambda. And so OpenBugs is going to complain probably that it doesn't really know where to start sampling on this distribution because it's very, very, very wide. And what we will do is just give it a couple of starting points in the sampling. And so I will actually specify some initial values on lambda just as a starting point. But remember, we typically throw away the first, I don't know, 100 or 1,000 samples. So it doesn't really matter for most problems where you start the sampling, because we're going to throw those away. The Markov chain is going to kind of march to the posterior distribution pretty rapidly usually within 10 or 20 samples, but nonetheless, OpenBugs requires us to give it a starting point. Hence my init section there. And so when you run this then, and we're going to keep track of the mean time to restore or recover, and then lambda, I end up with a distribution on both. And then I can get the mean values, I can get the 5th percentile, 95th, 50th, and so on. And so what you would see here then, given that I'm assuming an exponential model, given that I have these data representing some process, the failure rate or recovery rate, I guess it would be in here in lambda, has a mean value of 1.3 times 10 to the minus 3. And of course, it's uncertain. It has a 5th percentile from about 8 times 10 to the minus 4 to 1.8 times 10 to the minus 3. And we can plot out the distribution. So this is what the posterior distribution on lambda looks like. I also have a distribution on the mean time to repair or recover. So this says, on average, the recovery time is going to take, let's assume this is in hours, 860.5 hours, which is somewhere about right here. So 860 hours is the average recovery time or repair time. But it's uncertain. There's a distribution on that. And if you look at the fifth goes from 540-ish to about 1,395th. So with 90% probability, I know I'm between 539 and 1,320. Okay. And so I also know with 10% probability that I could be outside those bounds. I have a 5% chance of being above this, a 5% chance of being below that. And you could ask yourself, well, does that make sense? 860 hours. Well, if you go back to the data and start looking, yeah, you can calculate a mean just from those data points, but you notice there's a lot of variation. I mean, one of the recovery times, repair times, took 7,929 hours. That's very long compared to the ones. And again, this could be real data, could be made up data. I don't know. But 800 hours is not an unreasonable repair time on average. Okay. Oops, somebody's in the lobby. Hold on. Okay. Again, the exponential was just one kind of a model. We have other models. For example, if you're talking about time-related, say, recoveries or restorations, other models that you might run into are the Weibull or a gamma or a log normal. And so if you're going to use one of those other models, what you would do is you would just go back to where you have, instead of the exponential, it would be perhaps a log normal or a Weibull distribution there. Okay. And then once you substitute a model, you can actually check to see which ones perform better. And there are different ways to check. And the whole idea of model validation, there's a section in the textbook that talks about that in a lot of detail. And there are different probabilistic checks we can look to see which models perform better, which ones perform worse. Okay, let me move on to another new topic here. Talking about trending. So you might have data or a process that gives you data like this, where I'm running a facility. Maybe this is a case where I'm going out and operating many components, and I see failures and successes. And so I might be gathering data where I just have a fleet of components, or I could have say a fleet of plants too. I could have multiple plants that are all going to kind of pool data. For example, I could have, say, 20 nuclear plants. And in those 20 nuclear plants, I want to count how many times I see a loss of coolant accident. So that's one of the initiating events in a PRA model. So I'd go out and look out of those 20 plants every year, count how often that they're actually running, and count how many loss of coolant accidents they have. Now, of course, most years we never see a loss of coolant accident, so I'd have a lot of zeros. Maybe I'm going to count how many times the plants tripped, so transients. So for example, this might be an example of, okay, I have 20 nuclear power plants. In year one, let's just say this was 8 years ago. In year one, out of my 20 nuclear power plants, I operated in that year a total of 14.63 years of operation. So my 20 plants meant I did not have 20 years of operation because some were shut down, some were refueling, and so I had less than 20 years of operation. But let's say I had 14.6 years. During that time, during that year, I had 16 transients. So not a very good year. The next year, I do the same thing, I count. Next year, I had a total of 14.15 collective years of operation between my 20 facilities. I only saw 10 transients. The next year, I saw a little more operational time, so I had 15.75 years of operation between my 20 facilities, and I only saw 7 transients, and so on until I get to the 7th year of data collection, where I had 17.34 years of operation, and I only saw 2 transients. So we could look at, is this trend of transients, what does it look like? And I can look at that probabilistically. I could do a Bayesian update and do the trend all at the same time. Now, just doing an eyeball here, you would say the trend is that we're seeing a decreasing trend in the transient rate, because at least initially I was having a lot and now I'm not having so many. So maybe I figured out some problems I was having. But we can quantify that probabilistically. I don't need to just say it looks like. I can actually quantify the strength of that information. So I can calculate then the transient rate each year and then trend those in open bugs. So the rate I'm going to call lambda. And it's a little hard to see, but there's a number associated with each of these bars. So 1 represents year 1, year 2, year 3, year 4, 5, 6, and 7. Each bar, it's similar to the Band-Aid plot that I showed yesterday in Excel. This is a 5th, 95th, and a mean value coming out of open bugs. And what we're doing is, you can think of it, we're doing a little miniature Bayesian updating each year and then comparing all years. In other words, let me go back to my data table. When we set this up, we're going to take this first year and calculate the transient rate for the first year. So I had 16 events, 14.6 years of operation. Next year I had 10 events, 14.15 years of operation. I get 7 distributions. The red line is the mean value for over all the distributions. But you notice there is a trend. Again, I could just look at this and say that, but we can quantify that also. The distributions themselves change from year to year. Sometimes it's wider, sometimes it's narrower. But it looks like I'm moving in a positive direction. And this is an example of something that the NRC, the Nuclear Regulatory Commission, does, is they will look at component and different kinds of performance over long periods of time to see, is the industry getting better, worse, is it leveled out, for different kinds of questions. Let's look at a different example of data that you could trend. In this case, it's still, I'm going to have multiple years of data collection. But what I'm collecting here is not really failures or events over time, but instead what I'm collecting is number of failures that I see when I go out and test a component. So maybe I go out and 52 times a year I test a component. First year I saw 4, second year I saw 2 failures, 3 failures, and so on. Looking at the data table, it's a little hard to see here. This is not as extreme. Maybe the trend is getting worse. Maybe I'm seeing more failures, you know, in the more recent years. A little hard to see, but we do the same kind of calculation. We're able to take each of the years, set up a binomial model. For example, we could set up a Jeffreys non-informative prior, the data, and then get a distribution for each year. And again, this one is not as conclusive, but it kind of does look like there's a slight trend that the failure probability might be increasing over time. One way to kind of look at that is almost connect the dots in the mean values. You might have a line that looks like something like that, so a slight trend. So how would we model these trends? Well, again, that's just a different kind of model, an equation that we could put into the code, because the code is, OpenBugs is going to give us distribution for all of these rates over time. We could figure out, well, how do we want to represent that rate, which we call lambda, over time? So for example, we could have a linear model that just says, you know, the lambda starts out at some baseline, but is going to increase or decrease, you know, that this variable a here could be positive or negative. It's either going to increase or decrease over time. And so I could just put that equation right into the script, and OpenBugs then would do the Bayesian calculation for what's the baseline and how much is it changing each year. And it will also then determine, you know, is it a positive trend or negative trend? Because once I put an once I put this equation into OpenBugs, it will treat everything probabilistically. Now, T is not probabilistic. T is going to be 1, 2, 3. It's going to be each year. But A is just a variable, and it will have a distribution after I do the calculation. And so we'll know how strong is the trend. we will know if it's a positive trend or a negative trend, and we'll know the probability related to that statement. So very powerful concept. But that's one model. We could use the log linear model, or I essentially just take the ln of the linear. Could have a power model, extended power law. Again, these are all models. If you think you want to look at a specific model, put it in. You could test the strength of that model. The model may not work very well at all. It may work well. But the nice thing is it's very easy to do these calculations in OpenBug. So you can try many different models and get a sense of how they work. So if we want to look at, say, the log linear model, what that would look like in terms of OpenBug script. And again, the textbook has many, many more examples, but we're just hitting the surface of the textbook, kind of like hitting the surface of the iceberg, I guess. The model. So we have a set of data. Hence, you're going to see this for loop that says, okay, we're going to walk through the data. In this case, we're going to be going through the what I was calling the transient example, where I was counting the number of transients in my fleet of 20 reactors every year. That would be a Poisson aleatory model. And remember from yesterday, the Poisson is a single parameter model in OpenBugs. We need to specify how many transients did we see. We call that X. Mu, though, is lambda times T, or time. I'm calling S my time. I'm calling lambda my rate. That's mu. But you notice all of these are an array now because we're looping through each line of that data table. And then I simply put in a new equation here that says I want to come up with this middle one, a log linear model to represent the possible trend in the transient rate. And so to do that, it's simply the log of lambda, the log of those distributions, is equal to A plus B times I. And again, I remember here is the years. I is going to be first year, second year, third year. B then will be the slope of the trend. If B turns out to be 0, that says there's no trend at all. If B is negative, it's a negative trend. If B is positive, it's a positive trend. Okay, so I'm setting up the model there. And that's in a for loop. Now, also in the model then, I have to specify priors for everything. I then would have, for example, a prior distribution on A and B. Here, there's a special keyword that just says it's kind of like a uniform distribution across the entire range of possibilities. I don't know what A is going to be. I don't know what B is going to be. I don't know what my baseline is. I don't know my trend, and I'm not going to bias that. So I'm just going to tell OpenBugs, use just a flat kind of an infinite uniform distribution. Okay. And then these last two lines are just extra calculations that I'm going to do to be able to just show the kind of power of OpenBugs. So the first line here is there's something called a step function, and the step function is either 1 or 0 depending on what's inside of here. So if this expression inside the parentheses, if that turns out to be positive, the step function returns a 1. If it turns out to be negative, it gives a negative. And so what I'm looking for here is if I start, say, 0 minus B. So if B is negative, I will take 0 minus a negative number. I will end up with a positive value here, which gives me a 1. And so the more negative the trend is, the larger this value will be. And essentially what we're doing is each simulation we're looking to say, do I get a negative trend as an outcome or a positive trend? And I could turn that into a probability via the step function. Because what OpenBugs will give me then is really the ratio of how many times did I see a positive trend versus a negative trend. And it ends up being, and it's a pretty cool keyword, it ends up telling you the probability. In this case, it would be the probability of seeing a negative trend. And so that probability could be 0, could be 0.17, it could be 0.6, it could be 1.0, I don't know. But I'll be able to get a probability of the trend using a simple expression like this. So again, another nice feature built into bugs. This next line then, we're able to make predictions for future years. How do I do that? Well, remember I said the variable I here is my years. So 1, 2, 3, whatever. And I had, in this case, I'm setting up the problem to loop through I being 1 to n. So if I have 9 years, n would be 9. But I can, since OpenBugs knows all of these parameters all of the time, and it knows the distributions, if I know lambda, and if I know A, and I know B, I could ask it to make a prediction for year 10. So that's just n plus 1. So I could either say n plus 1 or put a 10 there, it doesn't matter. I can ask it to make a prediction for year 11, year 12. I can go out as far as I want. Very nice feature. So not only do I get the distributions on the transient rate as a function of time, I can also make predictions for what should I expect to see next year or the year after. Okay. So a lot going on in this one script, a lot going on. But again, with a powerful tool like OpenBugs, there's a lot you can do in a very compact form here. So when we run this analysis, what we see is, and this is just the data table part. I don't know if I plotted. Okay, yeah, I'll show you the plot here in just a second. But the data table, of course, I will get lambda as a function of time. Remember, time 1 is first year, time 2, all the way through 7 years of data. I get a rate. And so the first year, the rate of seeing transients was a little more than 1 per year. The second year decreased about 0.8 per year, and 0.6 per year, and 0.5, all the way down to about 0.23. And again, remember that, when we looked at the data, it looked like we were seeing a decreasing trend. And the Bayesian analysis supports that, of course. We can also then calculate what's the probability, and I didn't show that here. Sorry. Normally, so one thing you don't see here is I did not put out the trend option or variable. Trend would have been the probability that we're seeing a negative trend. I apologize for that, but it's a fairly high probability that we're seeing a negative trend. I could tell you that. And specifically then B is the rate. What is the rate of that trend? And so it's going down basically by 0.23 per year. And you can kind of see that in the data. And so if I ask for a prediction for year 8, it's going to be, this is a log linear model, so we're not going to go negative. We're not going to go below 0, but it would be maybe 0.01 or 0 something, 0.2. So effectively, if I took the year 7, took that value minus that value, that would be close to the prediction of year 8. But again, it's a log linear, so we start to kind of level off. Anyway, all of this is going on. The calculation literally takes a few seconds when we run that script. And we could do many other things here, but and again, all described in the textbook. Any questions on that? Okay, I'm going to finish this before we take a break on this slide here. And so this shows, again, a couple of things. This plot that you can dump right out of OpenBugs will show the distribution as in terms of these Band-Aid plots on lambda. So you see the rate the first year is pretty wide. Mean value is a little more than one transient per year. But we're going down. You can start to see the flattening out of the curve there. It will stay above 0 since it's a log linear curve, but year 8, I make the prediction and OpenBug simply puts that out. Year 9 would be a little lower and so on until we leveled out at some plateau. But and these kinds of plots are directly available out of OpenBugs. So again, a very powerful tool. Any questions?